Well, thank you very much, Greg, and I appreciate the opportunity to speak to you about a novel H2S control technology that we've developed at NewSky 4 years ago this month. My colleague, Yasmin Yeager, who's co-author, chemical engineer that works at NewSky, and I were staring at some very unusual iron-based solutions that were completely soluble at pHs where iron really should not be soluble. And so we were trying to figure out what we had done wrong, and we just realized that we had discovered a new way of solubilizing iron at alkaline pHs. If you know much about iron, it's essentially insoluble above about pH 6 unless you add lots of organic chelating agents. And instead, we've managed to solubilize iron using an interesting mixed metal iron carbonate complex. It's come a long way in that 4 years. This is one of our systems at a dairy in northeast Colorado, and if you're through the Denver or Boulder area, let us know. We'd be happy to take you out here and take you for a tour. I'd also like to acknowledge other co-authors of this talk. Paul Stout from Tetra Tech has been a huge help to us. Jared Walker from More Control Systems, who did a lot of the engineering, and Al Hislop, NewSky's chief engineer. I don't really need to tell this crowd too much about hydrogen sulfide, but I will say I agree with Craig that it's not the dominant odor around landfills. We've learned to recognize it, and the only times that I really smell H2S around the landfill is when we get a whiff of the biogas, which often contains very high amounts of H2S. It's a particularly pungent, foul smell. As you know, it's a deadly gas, and typically when we're around landfills, we're smelling something else, and there are a lot of colorful odorants, things like cadaverine and putrescine that I sort of suspect are the things that we're smelling around landfills. I'll tell you a little more about that later. So, yeah, as I mentioned, this is a water-soluble alkaline iron-based complex. That's a photograph of our lab with a flask of SulfurSolve, and next to it 14 totes containing each about 280 gallons of SulfurSolve at dairy in Colorado. So I can't really read my own slides, so I'll just kind of speak off the cuff here. Oh, I've got it in front of me. That's good. These computer things are so cool these days. Yeah, again, this is an alkaline mixed metal solution. It's an anionic complex. As you know, ferric iron is a +3 cation, but this complex is anionic. We proved that by checking against anion and cation exchange beads. The lean solution looks like the flask you see there. It's clear, it's kind of an iced tea color. The rich solution is just pitch black and opaque, just full of iron sulfide particles. And the operating temperature range for this chemical appears to be from down around freezing up to maybe 130 degrees. We've actually boiled this stuff, and it seems to do no harm at all. So I'm sure you're all familiar with the conventional methods of treating hydrogen sulfide. H2S scavengers are typically single use, or maybe you can get like one regeneration cycle out of them. They're often iron-based compounds or things like activated carbon. They react with the H2S. They're frequently solids, so you have a sort of surface area to volume problem. The reaction is occurring at the surface area, whereas you're also paying for the interior volume of the scavenger. So they tend to be very effective at projects that have either relatively small gas streams or relatively low H2S levels, because the capital costs for these scavenger systems are usually quite low. Biological processes, can be quite effective if they have steady, high H2S levels. There are a lot of bugs that like to eat hydrogen sulfide, but typically, particularly in places like Colorado, they're problematic because of temperature changes. They don't like spikes or drops in H2S level, and so they tend not to be as reliable as we'd like. And finally, there's a group of chelated iron technologies. You probably know them by names like LOCAT or Moro or Streamline. Those are probably the most similar chemistries to what we've developed at NewSky, and so I'm going to spend some time trying to distinguish our chemistry from these chelated iron technologies. Essentially, what they do is use chelating agents like EDTA to solubilize iron at high pHs. So this is sort of a market map. As you can see, the scavengers tend to work best at either small gas streams or large gas streams that just have small amounts of H2S. Beyond that, they become very expensive per pound of H2S treated. As Greg mentioned, $4 to $6, and we've heard numbers as high as $18 per pound of sulfur treated. Technologies, the chelated iron technologies are expensive capital costs and much lower operating costs, and so they tend to work best where you've got large gas streams with high H2S. And the biological processes cover a lot of this map, but again, they tend to be sort of unreliable because the bugs will decide one week that they want to go on vacation or something. SulfurSolve, which is what we've named this complex, covers a lot of this map. We've worked from 50 to 70 parts per million up to, just this last week, 185,000 parts per million, almost 20% H2S, and had good coverage of that entire range. So I'm going to talk about the chelated iron technologies. The molecular diagram you see in the lower left there, many thanks to Yasmina for coming up with that. That is ethylene diamine tetraacetic acid complexed around an iron atom, and that is how these chelated iron technologies solubilize iron at these pH ranges that are ideal for capturing an acid gas like H2S. So these are organic molecules. They are expensive to make. They're usually worth 3 to 4 times, or costs 3 to 4 times the cost of the iron that is sequestered inside them. Interestingly, our bodies use a similar method of solubilizing the iron in our hemoglobin. They use a heme complex that isolates individual iron atoms, and that's the difference between your red blood or blue blood, depending on how well oxygenated you are. These are the molecular mechanisms of capture and regeneration of these chelated iron technologies. 2 iron atoms are involved in electron exchange with a single H2S molecule. So those reactions are indirect. The electron transfer occurs across that organic overcoat, and as a result of that and the cost of the chelating agents, these chelated iron technologies typically are using low concentrations. They don't want to lose those expensive chelating agents, which tend to break down in the presence of oxygen, and you just don't want to lose them. So you use low concentrations, and you rely on the alkalinity of the surrounding buffer to capture the H2S. And then in the regeneration phase, there's a redox reaction that occurs that converts the captured sulfide into sulfur. And that's, in many ways, similar to our chemistry, except for the way that we solubilize the iron. So we named this process SulfurSolve, and this is how we're solubilizing iron. We discovered that if you add a large amount of an alkali metal buffer, particularly carbonate buffer, the carbonates and some hydroxides and the other metal coordinate around the iron and solubilize it at certain pHs and concentrations. If you use a solution that's too dilute in those anions, this precipitates out as iron oxide particles. And iron oxide particles are a major headache. They clog the sulfur. They have the surface area volume problems that I've mentioned before. So by reducing or almost eliminating the solubilizing agents that we use, we can significantly reduce chemical costs, minimize degradation effects. Again, those chelating agents are very sensitive to oxidation, and it allows for, most importantly, a direct molecular reaction between the H2S and the iron. instead of that indirect electron transfer between the iron and the H2S through that organic overcoat. This is direct reaction, and it's very fast, and it results in essentially completely eliminating the hydrogen sulfide that's in the gas stream. The only H2S that really escapes is H2S or gas that happens to, kind of run the gauntlet through the droplets of this chemical coming through the reactor. As a result of that very fast and very stoichiometrically favored reaction, we can avoid using even packing in a column. We can just have a rising gas stream of biogas with H2S in it and a shower of this chemical coming down from the top. And again, we're able to remove 99.9+% of the H2S. That reduces our pumping costs and simplifies our designs. So this is a basic process flow. It's rather similar to other H2S treatment technologies. There's a scrubber column. Again, we are avoiding packing because the formation of sulfur can kind of foul packing. And so we're just spraying this chemical into the top. And as long as the gas stream comes in contact with that spray anywhere in the column, it removes it. So we tend to use 2 of these columns in series, one with co-current flow and one with counter-current flow. But we've also, just used a single column, and in one case, just a 2-foot spray zone removes 75% of the H2S in the gas stream that contains 16,000 parts per million H2S. The spent solution is pumped over to a regeneration tank where we blow air through the media. I can tell you that at the top of that tank, what we smell is not H2S, or no H2S there at all, but we do smell that kind of characteristic odor of the landfill, and we try not to invite the neighbors to come up and smell the air, but it's quite faint when you get away from it. The sulfur is run through a filter. We use Oberlin filters, which remove the sulfur, and it forms a kind of light yellow sulfur cake that's about 70% dry sulfur by weight. I'm going to talk about several of our projects, but this is just a quick photograph of one of our systems at Deane, Colorado. You can see the component parts of it. This is the regeneration system, and this is a 3 or 4 stage system in which we're increasingly completing the regeneration process, blowing air through the media. And at the last stage, the sulfur is floated over a weir and goes into the filter, and the regenerated SulfurSolve is returned to the scrubber column. This is a little more about the sulfur. You can see some photographs of the sulfur cake in that bottom picture. It's kind of a light yellow, damp, dry, solid. It has no significant odor, and it can be used as a fertilizer, or potentially you could spray wash it, remove any of the remaining SulfurSolve, and use it as a source of a raw chemical. Essentially, in terms of maintenance and testing, this process is fully automated by our manufacturing partner, More Control Systems. There's periodic sulfur disposal. The sulfur kind of spills out into a dumpster-like device. Testing, we want to monitor iron levels and make sure that the iron is not gradually depleting. Obviously, the sulfur carries away some of this chemical, and so that has to be replaced. And we can spray wash it to try and recover as much as possible. We often will measure the pH or the oxidation reduction potential. We see a significant swing in both of those during capture. The pH swing is due to a sort of capture-release process involving the carbon dioxide. We actually remove about 15-20% of the carbon dioxide from the gas stream as well, which can reduce the cost of gas upgrading. And we also measure moisture content. We anticipate sort of semi-annual maintenance process on our systems to replace some pumps or clear out any fouling that may occur. I'm going to talk a little bit more about the next couple of projects. This was a pilot project we did at a landfill in Northern California in November 2019. 2019. We were treating gas that had about 700 parts per million of H2S. This site was spending, I think, close to $500,000 a year with a kind of carbon-based scavenger to treat the H2S on the gas that they were running through engines, and then they also were flaring a lot of this gas. We were on the flare side of the landfill. We dropped the H2S to much less than a part per million. In our general operation, we're treating only about 45 SCFM of gas, but that was because our blower was limited to that size. You can see here some of the data. Essentially, H2S was not detected in many of the treated gas samples. We saw, I guess, 1.3 part per million. These were samples that were sent away to the lab using ray tubes and Draeger tubes. We were essentially seeing less than half a part per million in almost all of the tested gas samples. This was a commercial scale operation at a wastewater plant in Wisconsin. It's a food waste plant. We had a third party, Burns and McDonnell, do an analysis of the technology, and they confirmed both the sulfur balance was 97% of the incoming H2S, and we were typically removing 99.9% of the H2S. Again, here's some of the data. And this site where we treated recently just purchased the system that we demoed there about a year ago. Okay, so this is another landfill site. This is in the Midwestern United States. If you recognize this as your landfill, I want to thank you for the opportunity to demonstrate our technology there and develop the technology, and also provoke the competing technology that you use there from contacting us and asking us not to make comparisons of the iron-based chemistry with their iron-based chemistry. So they reached all the way out from Europe on that matter. So this is a site where we were treating up to 100 SCFM of gas containing about 16,000 parts per million of H2S. And when operated at that system spec, we removed the H2S to non-detect levels in the ray tubes. Essentially, dozens and dozens of ray tubes showed no detectable H2S. They were, I think, 1 to 150 range on the ray tubes. We also measured in the regen airstream. We wanted to know, are we carrying over and releasing some methane to the air? We were not able to detect methane in the regen airstream, nor was there any sulfur-based compound, either H2S or SO2 or anything like that. Again, there's a little bit of odor, and it's some of these more complex constituents that are associated with landfills. Craig could probably tell you what they are. So here you see kind of a lineup of some of those ray tubes with no detectable H2S, and you see a gas monitor that I think can go down to about 0.1% of LEL, which I think is maybe 50 parts per million of methane, and we're not seeing any methane in that airstream. Let's see, you can see getting from 99.99, I don't need to look up there, 99.99% capture. If you see on the left side of that table, those are sort of depths of packing that we were using. And with the 10-foot depth of packing, we were getting 99.99% of H2S capture. Again, this was 16,000 parts per million in. Additional testing, Yasmin and I spent about a year in the laboratory working on this, and we were consistently startled by how efficient it was at capturing H2S. At one point I put our tank gas, which is 100,000 parts per million H2S, through a small cylinder with a sparger at the bottom, and then I backed it up, this being 10% H2S after all, with a second column that had SulfurSolve in it. And it just remained its characteristic red iron color or orange iron color, and you couldn't even smell the H2S that came through the first column. Obviously, you can't do that for very long, but it was complete capture. We did a 7-month pilot project at the Boulder wastewater plant, typically with fairly low H2S levels, and it worked very consistently there. We didn't have any fouling problems or anything associated with that. We did another project at a pulp and paper mill with, I think, 16,000 parts per million of H2S. Again, dropped it down to 1 ppm. And then more recently, Yasmina's been doing work with our partner, More Control Systems, at an amine acid gas site near San Antonio, Texas. And that has 120,000 to 185,000 parts per million H2S. Here are some installed commercial systems. We have a small unit that's at a California dairy pilot site in the Central Valley. 3 big systems. You saw one of them on the cover slide at dairies in Colorado. And Varesco AD is the site that we did our demo a year ago that recently bought the skid that we tested there. So the characteristic, as a scientist rather than an entrepreneur by nature, I spent the first half of my startup career being told, don't talk about the science, talk about the business. Forget the science, nobody's interested in that. So once you have something that's really successful, then everybody says, talk about the science, don't talk about the business. So forgive me if it's a little schizophrenic, but the characteristics of an ideal H2S control technology would be low operating cost, non-toxic chemistry, sustainable, stable operation, reduce hydrogen sulfide to near zero, convert H2S to a useful resource, and continuous regeneration of the H2S capture chemistry. And I would be happy to entertain any questions on whether or not our technology kind of meets that standard. And finally, I just want to thank More Control Systems, which built the large skids that you've seen, and Jessica Moore is here, who helped us with that process. And so she is their marketing director and part of the family. So they've just done a great job with us, and we're happy to be partners with them. Thank you very much.